Hello, so today I'm going to talk about how to make some basic scientific graphs in Python. So these are some of the packages you're going to want to install in your Jupyter notebook. And these are some of the parameters that you can adjust to make your figures more publication grade, especially upping the DPI and setting font sizes and tick label sizes. And this is an output function that you can call at the end of any of the graphs you're going to see today to actually write them to your system so that you can import them into some graphic design software so you can actually make the panels. So getting into it, we're going to make a bar plot first showing genes with expression changes between two conditions. So I'm going to simulate some data here in Python, but obviously, whoops, you can use your own data from your experiments, and this is what it should really look like. This is a long format where we have a bunch of different genes with two conditions and multiple expression levels. So we're going to make a bar plot and put the genes on the x-axis, the expression on the y, and we want to color them by condition to separate them. That's what you set the hue parameter to, and specifically we're going to color the control some blue and treatment pinkish, and I'm also going to get rid of the top and the right splines so it'll reduce the visual clutter of the plot. So if I run this, we get a nice little bar plot here, and you can see the expression changes between the control and the treatment for a bunch of these genes. And individually, you can use slicing to do statistical tests between the control or the treatment, or even calculate your fold changes. So now we're going to move on to the line plot here. And here I simulated some time versus drug concentration data for 3 different drugs. So maybe you can use this to make your hill plots or find IC50s. So with the line plot, it's a little different, but the concepts are the same. We're modeling time data with different concentrations, and I want to color the plots by drug. And this will change the thickness of the line, make it easier to see. And I'm also placing a horizontal dashed line at 50% of the concentration so that you can get an idea of this. You can also set your title and move the legend, and I'm again taking out the splines so you can see a clear relationship here in this line plot, and you can get the idea. There's also other tweaks you can do, but you could ask ChatGPT or Google to do this, but again, this is just how to do it properly and cleanly. So moving on to the scatter plot here, we are going to look at the relationship between dose and some sort of gene expression for a couple different samples here. So whenever you move on to the scatter plot, this is really between two quantitative traits, and you can color those points by their categorical sample. So again, it's the same deal. Dose on the x-axis, expression on the y, and you color your hue. But also for the scatter plot, you can make the points bigger if you change this S parameter. So I have it at 10 now. I think it looks fine. And you can also change the edge color or the boundary of the plots any color you want. And if you add like line width to this, you can change the thickness of that border on the plots too. And what you can see here is that these data tend to correlate together. As you increase the dose, you're increasing the relative expression of this. So a different kind of scatter plot you can show if you want to more get into the relationship is called a reg plot. It's like a regression plot, and you can see your regression line and kind of look at your fit here. This is where you can also do some Pearson correlation or Spearman, whatever, and show the relationship. like that. So moving on to box plots, this is if you have sort of a distribution data for multiple different categories. You put the categories on the X and your different expression values or quantitative values on the Y, and you can also separate them by tissue or your categorical. And this parameter here, show flyers, how the box plot works, it's different quartiles of your category or your quantitative distribution. And if a point falls outside of that, it's considered an outlier and it'll show up as a circle on the plot. Sometimes they're pretty distracting or they don't make sense, so you can just hide them for this, as I'm doing here. And this line width will also change the thickness of the lines in the actual box plot. And I would also recommend for these setting the Y limit, especially if your data doesn't start at 0, so it better communicates what's actually going on with your data. So as you can see here, we have distributions of gene expression for the liver, the brain, lung, and kidney here, simulated of course. And another popular plot is the violin plot. So you use this function and you can specify what the statistic is being used to calculate this plot. Here I'm using the quartile and it's the same thing. However, these plots kind of give you an overextension, so as you can see I had to increase the Y limit from 10 to 13 to make sure everything fits within the plot. And finally, we have the heat map here. So this data kind of has a different layout compared to other datas. As you can see, we have two quantitative axes. This is more of your matrix format. So genes on the y-axis and samples on the x-axis here, whereas in other ones you kind of have this long format. So that's something to keep in mind of. So the data should look like a heat map. And now we're going to color it in with the heat map function, and these are a little unique compared to what we've seen already. You put in the data. This center is where the center of your data is. Like for fold change, the center would be 0. And if you use a binary heat map, it will color it so that, say, red is upregulated and blue is downregulated. And you would specify that here, like what color map. You can Google different color maps to use for this, like what I was talking about earlier. A binary heat map would be like cool warm or BWR. Here I'm just using a magma heat map, and you can set it to be square if you want all of the different cells to be visualizable and not kind of squished and doing weird things. You can set a line color to separate those cells and get a line width, of course, and you can also annotate them and change the formatting of that. But this is what that will look like. And finally, this is a little more advanced plots. In Python, these are kind of a little finicky to get working, but I think that they are good for interpretation. These are the cluster maps. It'll apply hierarchical clustering to your X and Y axis to show you more trends in the heat map. I'm a big fan of these, but again, they're finicky. All that's really different is you specify the actual size of the figure here as opposed to using this function here. And you can specify the sizes of the actual dendrogram or the actual clustering in the plot. You can position the color bar, and you can use a clustering metric. Here I'm just using correlation, and the plot will look like so. You can see some of the differences here. Like it'll put sample 1 and 5 together and show that, hey, gene 2 is kind of the same color between these. So I hope this quick rundown was beneficial to helping you make figures. Thanks for watching.